This example I want to use for two-dimensional orthotropic material and to show the principal directions of this stress are not in the same directions of the principal strength for orthotropic material. Okay, so here we can try is this the given orthotropic material, and here we are given Ex equal to 147 MPa. Silly. Let me do it again. 4.7 GPa. 1 GPa. Okay, we are given material properties like this, and also we are at the point we measure the stress. This one equal to 7 MPa and sigma y1 2.1 MPa, sigma zz minus 2.8 MPa, and sigma xy equal to 1.4 MPa. Okay. So the question is this: we want to determine the principal directions of the stress and the strain. We want to determine the strain component. Okay, so the first one, we want to determine the strain component. Then once we have the strain, then we want to determine the principal directions of the stress and strain individually. Again, for this one, we simply apply these equations here, okay? And not to rewrite the equations. And here again, we simply plug in all the information here. For these equations, again, this one, let me highlight this, and this can be directly used to build up this equation to calculate for the contents of the compliance matrix. So in this way, we are given the stress, we can calculate the strain, normal strain directly. And for the three part, that is about the shearing strain. For shearing strain, we have such equations. Either we using engineering notations, sigma xy, sigma xz, sigma yz. Okay, so this portion is to constitute the shearing stress-strain relations, and this one is about the normal. And again, for orthotropic materials, basically the shearing and normal deformation stress, they disengage from each other, so we can deal with them separately. Okay. So basically the whole things we can solve for, and then here for stress. here, from here we can determine the strength equal to 520 times minus 6 yy. So now we fix this one and strength component. Now we calculate the principal directions of this stress. So now the principal directions. How do we approach these questions? So this one is in our content of stress. This is a three-dimensional stress, right? So for this one, the listed are non-zero stress component, and there's other here is 4. In total, we know the stress component is this tau ij equal to tau 11, 2, 2, and 3, 3, right? 1, 2, and 1, 3, and 2, 3, and these are symmetric. So in total, we have 9 components, and here we are given is this. This is 7, and yy is 2.1, and zz equal to minus 2.8, and also we are given xy equal to 1.4, and the remaining are 0. So we are given this one. Are you able to calculate the principal directions? Yes, right? How to do it? So get it? The typical way is this. We solve for the eigenvalue problems. Tau ij minus, for example, the principal stress is sigma, multiply with the principal directions x, and equal to, sorry, we let n equal to L1, L2, L3 be the principal directions. Okay, then the problem, eigenvalue problem is this, tau ij and with Li and equal to sigma times Li, right? So basically that's why solving is sigma ij minus sigma I and times Li and equal to 0. So if you calculate it, you determine the ij minus sigma I, and using this one, this is a typical eigenvalue problems. You solve for this one to determine the sigma, and that's supposed to have the 3 values, sigma 1, sigma 2, and sigma 3. 3 principal stresses. And for each principal stress, you plug in here to determine Li, and Li is the principal directions, and you have 3 directions. I try to recall your memory. Okay. This is a typical way, and you can do it, and that we've been exercised. On the other side here, I want to utilize one observation. One observation is this. For this stress component, you can see in this directions, For example, let me say this is the x, y, z directions. In the z direction, we only have the normal stress is that is compressive 2.8 MPa, right? At least in the z direction, there is no shearing stress component. So z direction, per our definition, what is the principal directions in which the shearing stress components are 0? So in the z directions in this plane, you see there's no shearing, right? So right away we can identify one of the principal direction in the z direction we are given here. Good? Okay, so the remaining is this. Basically we have determined z, then the remaining is this. We simply about the z direction, assuming this is the block. Okay, we simply rotate about z direction to a different orientation, then we can obtain the other two by rotating x, y to certain orientation. So under these situations, then we can see is this. By such observations, then z axis is one principal direction. Then we don't need to go such rigorous progress, and from here we identify this one, and then the sigma 1, the principal stresses, is minus 2.8 MPa. Okay, so down this one, then the remaining, the two direction will be happening in the xy plane. Now our efforts is looking for in the xy plane. So for xy plane, and that basically constitutes is by that component. Okay, so that component basically we can use Mohr circle. Mohr circle is easier, right? For Mohr circle, right now I'm talking is very practical engineering calculations. We don't have to go to mathematics. This one sometimes lacking some kind of physical insight of the problem. Just do it, right? Okay. So using Mohr circles, the stress element correspondingly in the xy plane. Okay. So basically here we can say the sigma x equal to 7, sigma y equal to 2.1, and then sigma xy, you usually use tau xy. Okay, sigma xy minus 1.4. Okay, using Mohr circles, and Mohr circle, I want to keep this one. Let me move to it. So if you remember the Mohr circle, basically that is really a circle. That's really tedious. And to determine the location of the circle in the stress and the normal stress and the shearing stress plane, we need to determine the centers. The center of the Mohr circle is at the average of the normal stress and 0. Okay, so for this case, the average is at 4.5 and 0. And also we determine the radius. The radius, basically that one, if you remember the formula, sigma xx minus sigma yy, 2 squared plus sigma xy squared. Okay, that is a calculation of the radius. And for that one, we've been calculated is 2.82. Okay, from here we can precisely locate. So from the centers to the vertical axis is 4.5, radius is 2.8. So here I can precisely locate, and this is the sigma xy with such annotations. Okay, and this is sigma y in these notations. Okay, and now we want to turn on the Mohr circle, determine the principal directions. So under this case, we have to label the status of the point on the x-plane. So x-plane constitutes a sigma xx and sigma xy. So for this one, the x-point is sigma xx, that one equal to 7 and 1.4. Okay. So this is an X point, and that located at 7. So this is 4.5 here. So 7 will be something about here. Okay. Now how about this one? This one is the positive, the normal strain, the positive strain stress, and that strain stress, if we plot it, that can be like this. This is XY plane, and this is our normal stress in X direction 7, and 1.4 positive by side convection is like this. Okay, so this one, basically this component has a tendency to rotate this element counterclockwise, so that direction is this. So this point X must be located in the fourth quadrant here. Okay. And in a similar way, Y point constitute a sigma YY. If you forget this one, I think you need to refer to the lecture notes, and this one you must know it, okay? And that is a minimum requirement here. So this one is YY equal to how much? 2.1. And the same, this one is 1.4, okay? So YY should be here. So let me make a diameter, this is 1. Okay. So under this situation, you can clearly, if we choose the acute angle for our calculation, this is 2 theta p. Okay, by looking at this triangle here, and this is 2 theta p, and this is r, equal to how much? Doesn't matter. Okay. R equal to 2.82. And how about this? This one basically is given by 1.4. So from here you can see sine 2 theta p equal to 1.4, 2.82. So from here we can determine theta p value. The theta p value will be equal to, where is my calculations? 14.9 degrees. Okay, and this one is clockwise. Now, in a similar way, we calculate strain. So strain has these things, and again, observing the strain component in the from the two component here, basically that means equal to gamma zx. This is gamma zy. Okay. The same thing, by observing this, we conclude the z directions is also one principal directions of the strain. Okay, so by observing this one, here we can also use Mohr circle for the plane strain condition based upon the 4 components here. So again, for looking for strain, here is the quick summaries. So again, for strain, that is a circle here, and this is the normal strain. And now I want to determine the vertical axis for shearing strain. So the calculation is the center in the similar pattern here, like this stress is the average of the normal strain and 0. That one. How much? 3573 divided by 2. Can anyone do it quickly for me? 35, 75, 70, 35, 73. So 18, 14, 8, 6. Five. It should be right. Is that right? Whatever, you double check with these numbers. The radius is calculated by epsilon x minus epsilon yy. No, I want to complete it, otherwise my mind will hang here.
It's 17,865.
865, okay, only less than 1%
Yep.
difference. It's good enough.
Good enough.
Good enough, thank you. And this one is divided by 2 and plus. What is this one? Again, that is a similar way. That is strain component square. Elastic strain or engineering strain. Okay, let me go square. Here is the strain stress square. Do you have any notes for this? Okay, let me type using this one, okay? So for this one, we can calculate, and that radius is equal to oops, I don't have that calculations. Can anyone do this calculation for me quickly? So this will be 25 divided by 2, 1200, about 1200. And plus this one half square, 75 square. How much? I don't follow me, okay? You do what?
Yeah, I know. On gamma, so we divided by 4, right? Because gamma is 2 epsilon.
Just give me a number.
I got 1320. So what you got? $13.20 is what I got.
13.
Yeah, 1320.
Very close. Very close. Because my calculation is something 200. That is 14. Yeah, very close. Good. So with this one, then we can proceed the whole things. Then, okay, use the 10 to the minus 6. So the center is here, and with the radius 1320, so the center is 17, so radius is only here, so that we can locate the axis is like here. Okay, so from center to here is, let me say 1786.5, and let me say this is 10 to the minus 6. Okay. And the radius from here to here is 1320. Okay, in a similar way, here in our notes, I like to use is using epsilon xy. Okay, using epsilon y divided by 2. Okay, let me use these notations here. No. Do you have any notes about the calculation of the strain? I think I made a mistake here. I want to correct the mistake. The mistake should be this. This one, this term must be only epsilon y. If you have that formula, this term should be the radius. If we using engineering information, that should be xx minus yy divided by 2 squared plus gamma xy divided by 2. I think that is what I intend to write. Okay. So here for this one, if we use an epsilon, the elastic strength, then only have this portion. So sorry, we have to multiply this one. So 144, 2, 2, 5, and 3, 6. I think about 1800 something. Can you quickly multiply those numbers for us?
1469.
That last epsilon xy. Oh, yeah. So epsilon xy. So this one. So this term should be 700, right? Sorry.
When I did it before, I divided gamma by 4 because it was a half.
Yeah.
So now dividing gamma by just 2 comes out to
1469.
69.
Okay, almost 1460. Okay. So this one radius 1460. Okay, so we hear the same thing. Then we can proceed the calculation for xy. Then label with x is the epsilon xx and epsilon xy here. And again, here we use these notations. For this one is x, the xx equal to 520, and epsilon xy equal to about 724, and times 10 to the minus 6, the micron unit. Okay. This one is positive. Again, that corresponding is this. We have xy. This is undeformed element, and corresponding to a positive strain. For positive shear strain, the corresponding deformation is something like this. Okay? The corresponding deformation for positive shear strain will be like this. So in the x directions, the shear strain is the angle from here to here. So that angle is to describe the change of this line in the x direction to here. And that change of the in angle is counterclockwise. So that is the direction we identify here. So for this point, that x must be in the fourth quadrant. So that would be 520. 520 should be something about here. So let me get a larger circle here. Okay, 500 should be something here, and then 700. So that one x should be here. Okay. Then x here, then corresponding this y point. The y again, the y is the constituted by strain in y direction and the strain. So this one is y, and we can copy that one 3053, and this one again 724. Okay, in the y directions, you can see the shear strain is changing in that direction. So here we label in clockwise direction. So y would be in the first quadrant up there. Okay. So once we identify these things, then here we pick up. This is 2 theta p. Okay, and in a similar way, we can determine the 2 theta p using the triangle. If you utilize this triangle, this is 90 degrees. Utilize this triangle here. So this is the radius, and this height is by epsilon y 724. So from here you can determine the 2 theta s and sine 2 theta p equal to r and 724, and our r equal to 1 for 70 and 724. Okay. So by these calculations, then this one will be equal to 15.23, and this is clockwise. Compared to our previous calculated principal directions for stress, and that is about 14 something. And for strain, that is 15. So using these examples has quite a few purposes. One is to rehearsal our calculation for principal stresses, principal strains. And then I want to also emphasize for orthotropic materials, the principal directions of the stress won't align to that of the strain. And that is a very important concept. And before, when you learned exposed to the older calculation for isotropic materials, then the direction must be together, must be aligned to each other. And you can use example to verify this. Okay, although we haven't gone to the isotropic material yet, but this is a quite a important concept for this. Okay, so.